Okay, so let's get started with today's discussion. Today we are going to be looking at the Chem 100 Experiment 10, Chemical Reactions and Chemical Equations. To this end, first and foremost, let's show where we're going to find this lab activity. So this is in the Chapter 5 Laboratory module. Here, as you can see, under Chapter 5 Labs, we have the Chemical Reactions and Chemical Equations Laboratory. Additionally, we have some pre-lab lecture recordings for students to review, and we have the report submission page. So here's what the Experiment 10 Canvas lab page looks like. This contains all of the data that we're going to be using to complete our report. Here is the pre-lab lecture Canvas page, which contains some information that will help you both engage with the laboratory, some instructions to help complete the lab experiment, as well as a pre-lab lecture covering the theory behind this experiment. Finally, there's the report submission page, which is where you're going to be submitting your full report sheets. So, one thing I do want to draw your attention to is in the experiment 10 page, before we begin this experiment, we're going to first and foremost make sure to open up our lab manual and find this experiment in our lab manual. So I've taken the liberty of pulling up the laboratory manual. So here is experiment 10, chemical reactions and equations. So there's a lot of preliminary information that I would encourage you to read in both the lab manual and in the Canvas lab page. So as you can see, there's a pretty long introduction section covering the background and theory behind this experiment. I would encourage you to read through and engage with this preliminary reading in preparation for the laboratory. We also have the experimental procedure, which is what we're going to be following through. And then all the way at the end of the lab manual, we have the pre-lab questions that you'll answer and complete before beginning the experiment. And then we have the report sheet, which I've taken the liberty of translating it and placing it into my drawing program. So that way, as we work through this experiment, we are able to write down our observations onto our report sheet. Now, the observations that you write down for this experiment may be a little bit different. This is a qualitative laboratory. So whenever you write down any observations, try to write it as much as you can in your own words. So we have this full report sheet. We have our experimental procedure. Now what we're going to do is we're going to go through the lab page after reading the introduction, of course, and we're going to go to the experimental procedure section. So here we go. We're in the experimental procedure section. This is where we're going to be watching some videos, engaging with some information on different chemical reactions, and then we're going to write down our observations. So let's take a look at what's happening here. In the lab manual, this is the reaction of magnesium and oxygen. We're going to take a piece of magnesium. We're going to in turn ignite that magnesium, and we're going to observe the results. If you were paying attention from prior lab experiments, you will notice that we've actually run this reaction before. This is the synthesis and preparation of magnesium oxide. So let's take a look at this video, and we're gonna speed through some of the parts to really focus on what are the pieces of evidence that we can use to show a chemical reaction is occurring. Okay. So here is our magnesium ribbon. They're taking it in a crucible and they are heating the magnesium ribbon. Okay, they're using a reasonably strong Bunsen burner flame. And I want you to pay attention to what's going to happen once the crucible gets hot. You'll be able to see it. Okay, let's pause there. Now, thankfully, this is being screened through a camera. If we were running this lab face to face, you would not want to look directly at the magnesium as it is undergoing this reaction. As you can see, it's glowing, not just because it's hot, but also because it's generating a large amount of light. So, as we can see in this chemical reaction, one piece of evidence that we could write down, the initial appearance of the magnesium is almost silver. Evidence of chemical reaction, we see a lot of light. The sample is glowing. And as we allow this reaction to proceed, let's pay special attention to what the magnesium looks like at the end of this reaction with oxygen. Okay, so magnesium's heating, continuing to heat. As you can see, it's still glowing, not only because it's at a high temperature, but also because this reaction generates a fair amount of light. Okay, so eventually the reaction is going to finish, and we're going to be able to view what does the sample look like at the end of this reaction. So they're going to do another heating cycle, and let's just skip to the point where they take their finalized sample. Okay. So, looking inside the crucible, the magnesium looks quite different compared to when we started this reaction because it's no longer magnesium, it's magnesium oxide. And we can see that because there's a huge change in appearance. So let's write that down. There is a change in the solid appearance. An example of this, it was a solid that is shiny, and it has been converted into a dull gray powder. So clearly, there has been a change. We went from magnesium to something that is clearly not pure magnesium. In fact, this is a new compound, magnesium oxide. We're going to take this chemical equation. So in this case, we have the following balanced chemical reaction. In terms of the type of chemical reaction, we have magnesium and oxygen combining to yield magnesium oxide. So this can be called a combination reaction. Or there's another type of reaction that is applicable. In this case, you have the reaction of a metal or other compound with oxygen to yield oxide products. It's also reasonable to call this a combustion reaction. And in fact, both of these descriptors are reasonable descriptors, though I prefer combination, as that is the more precise descriptor for this particular reaction. Okay, so we completed the magnesium and oxygen portion. Let's now take a look at our lab manual for the next part. So here we're going to look at the reaction between zinc and copper 2 sulfate, which, as we'll see in the video, copper sulfate has a beautiful blue color, and it's really a useful solution for a range of different reactions. And what we're going to see here is an example reaction that's often used in electroplating and other metal-based reactions. So this is quite a interesting reaction with a very easily distinguished visible Q. So in this case, they're going to take some copper sulfate, react it with a piece of zinc metal, and over time, the reaction is going to occur, and we're going to note any changes that occur as a result of this reaction. So here's our video. So here we have the copper sulfate solution being generated. As you can notice, it has a brilliant blue color. This is often characteristic of dissolved copper 2 ions. That metal piece is a piece of zinc. And let's now note just the appearance. The copper sulfate appearance, we note that it's a blue solution, and the zinc appearance is a shiny gray piece of metal. Okay. We're going to allow some time to pass, and this video has been sped up. As you can notice, those bubbles that are happening on the surface provide us some evidence that a chemical reaction has occurred. And as you can see in the video, the recorder has taken a piece of zinc that was left to sit in the copper sulfate for a long time, and they've set it up so there's a side-by-side comparison. So on the left is a piece of zinc that has just started to react with the copper sulfate, and on the right is a piece of zinc that has been allowed to react with copper sulfate for an extended period of time. As you can notice, after a long amount of time and after at least 30 minutes of reaction, the zinc now has this layer of a dark deposit on it. As you notice, the zinc has changed color. Something has been deposited on the surface of the zinc. And in fact, if you were to take the dark sample on the right and scratch it, you'd be able to scratch off the layer that has been deposited on the zinc and reveal that on the inside you still have zinc that hasn't reacted. So what's leading to that dark color? That's actually the copper ions that are reacting with the zinc and depositing on the zinc surface as copper solid. And in fact, if you were to break up the zinc and mill it into tiny pieces, you'd be able to collect and observe that you'll start to see solid pieces of copper powder precipitate out of this solution. So, commentary aside, let's after 30 minutes, the copper sulfate appearance, it's still blue. If you added a lot of zinc, you'd be able to slowly remove the copper ions and the solution would start to turn colorless, but that takes a lot of zinc. After 30 minutes, the zinc goes from a shiny gray solid to more of a black or brown solid. So in this reaction, in terms of balancing, this is a classic displacement reaction. The number of atoms of each element on each side are perfectly balanced, and this is known as a displacement, also known as a single replacement reaction. Okay, now we have a series of reactions between metals and hydrochloric acid. And I really like this demonstration because it helps you can understand why, in terms of making buildings, why we often prefer to use copper, and in the past, why we used lead for piping rather than other metals. And you'll see that when we observe the reaction of these metals with hydrochloric acid. So let's read our procedure. So we're going to take some test tubes. We're going to obtain a piece of zinc, copper, and magnesium, describe the appearance of each, and then we're going to place 3 molar hydrochloric acid into each of these test tubes, and we're going to observe the result. Okay, so here's our video. In this case, there are a range of different metals. So we have tin, iron, magnesium, copper, and they also have zinc and calcium. We're only going to focus on the metals that are important to us for this experiment. So let's write down our observations. So in this case, zinc is a shiny gray metal. Copper is more of a shiny brown metal. And magnesium is also a shiny gray metal. But don't worry, things are going to get quite exciting. So in this case, let's see how magnesium reacts with hydrochloric acid. As you can see, almost immediately, we're observing quite a violent reaction. As you can see, there are plenty of bubbles generated. When we look at copper, copper doesn't appear to be doing much of anything with the hydrochloric acid. Finally, for zinc, again, we notice another relatively violent reaction. As you can see, we're generating bubbles. And then finally, calcium's not on the list, but calcium, as you can see, the reaction for calcium with hydrochloric acid is extremely violent. Now, in addition to the fact that if a metal reacts with hydrochloric acid, you're also going to see the generation of gas. This is hydrogen gas. Also, as you notice, especially in the magnesium example, the magnesium metal is beginning almost to disappear and dissolve. That's because as the magnesium reacts with the hydrochloric acid, you generate soluble magnesium chloride in addition to the hydrogen gas. So we're going to write down our observations and provide evidence of chemical reaction. For zinc, the evidence of chemical reaction is the generation of bubbles / gas production. For copper, we see no observed reaction. Part of the reason why we use copper in our pipes is that it's relatively resilient to reactions with acid and other corrosive materials. Finally, for magnesium, we observe gas production. And then I'm just going to note that this is a vigorous or very rapid reaction. As we observed for magnesium, the moment we added the hydrochloric acid, it started bubbling like crazy. In terms of balancing each of the reactions, we have to look at balancing hydrogen. We have 2 hydrogen atoms on the right, so we need 2 hydrogen atoms on the left. These are each examples of displacement reactions, and these are specifically known as hydrogen displacement reactions. So for each of these reactions, as drawn, these are displacement reactions. Specifically, they are single displacement reactions. You could also call them gas generating reactions. Because they are, in fact, generating gas. Okay, let's move on to part D, reactions of ionic compounds. So here, we're going to look at a few more reactions. For the first one, we're mixing calcium chloride and sodium phosphate. Okay, so here's our test tube, and we're going to see what happens when we mix calcium chloride, which initially looks like a colorless solution, and sodium phosphate. As we can see, we're generating a solid precipitate, and the solution starts to adopt a cloudy appearance as a result of the fact we're generating this white solid. Okay, so in terms of the initial appearance, both of these solutions are colorless. And the evidence of a chemical reaction is that we see solid generation. In this case, we observe a white precipitate. In terms of balancing this equation, we have to balance the number of each ion. We have two phosphates on this side, so we need two sodium phosphate to balance phosphate. We have, in terms of calciums, three calciums on this side, so we need three calcium chloride to balance calcium. As you see, we have 2 times 3, which is 6 sodium and 6 chloride on the left. So we need 6 sodium chloride on the right. This is known as a double displacement reaction. These are also known as exchange reactions. And these are also known as precipitation reactions because we are generating a solid precipitate product. Okay, let's look at another reaction, this time between iron 3 chloride and potassium thiocyanate. So looking at our procedure, we're going to mix the iron chloride and potassium thiocyanate, and we're going to observe the results. Okay, so let's do just that. So we have the iron chloride solution. As you can see, it has a yellow color. We are then going to mix it with the thiocyanate solution. And this is often going to result in a pretty dramatic color change as we generate a new product. So as you can see, there's quite the dramatic color change as we generate the iron thiocyanate product. So let's write down our observations. The initial appearance of the solution, the iron 3 solution, is yellow. The thiocyanate solution looks somewhat colorless to me. And then evidence of a chemical reaction, there is a color change. We went from yellow to red. In terms of balancing this equation, again, we're going to balance by counting ions. We have 3 thiocyanate ions on the right. So we need 3 thiocyanate ions on the left. In terms of chlorine, we have 3 chlorine atoms on the right. So we need we have 3 chlorine atoms on the left. So we need 3 chlorine atoms on the right. In terms of what type of reaction this is, it's not a precipitation reaction, no solids being generated, but this is still a double displacement. Because we have an exchange of a pair of ions between two compounds. And as you can see, we take 2 unique ionic compounds and generate 2 new ionic compound products. Okay, let's move on to part E, sodium carbonate and hydrochloric acid. So in this case, we're going to look at a reaction between hydrochloric acid and sodium carbonate. So here they have hydrochloric acid. We're going to mix the hydrochloric acid and sodium carbonate solutions, and we're going to observe our result. So as we see, we have 2 colorless solutions. We mix the hydrochloric acid, and now we're beginning to add the sodium carbonate. And as you can see, almost immediately, we observe bubbles. In this case, the gas that we're generating is carbon dioxide. So let's write down our observations. So hydrochloric acid is colorless. In this case, we're using a sodium carbonate solution. So these are both colorless solutions. The reaction's the same whether the sodium carbonate is in solution or as a solid. In terms of evidence of a chemical reaction, we see gas generation. In this case, it's carbon dioxide. Now, to answer the question, what are they mentioning with regards to the burning match or splint? So when you generate a gas such as carbon dioxide, if you were to take a splint and light it on fire and put it into your test tube, what you'll notice is that the splint will immediately be extinguished because the carbon dioxide crowds out a lot of the oxygen in the container and you can't sustain a combustion reaction. So that's what the match or splint test is doing. We aren't doing the match or splint test in this one, but because we know the gas generated is carbon dioxide, we'd expect the flame to extinguish. You can also leave this section 3 blank because we're not going to do the flame test for this particular lab. In terms of balancing this equation, the first thing we want to focus on is hydrogen. So we have 2 hydrogens on the right, so we need 2 hydrogens on the left. From here, we have 2 sodiums on the left, so we need 2 sodiums on the right. Now, in terms of types of reactions, sodium carbonate is known as a base, hydrochloric acid is an acid, so we can call this an acid-base reaction. You can also call this a gas-generating reaction. And this can also be called a double displacement. All of those are reasonable assignments. Okay, let's look at part F now for hydrogen peroxide. And we're looking at the reaction of hydrogen peroxide and potassium iodide. For those wondering about this extra video just showcases the principle of conservation of mass. Whenever you run a reaction, the total mass doesn't change before or after the reaction. So if you captured the carbon dioxide in a balloon, the total mass of gas that you collect and the total mass in the reaction is the total mass of the reaction is going to be constant throughout the reaction. Matter isn't created nor destroyed during reactions. This is a very fundamental principle in chemistry. And this video helps demonstrate this in a very tangible way. Let's take a look at this video before we move on, just because I find it quite instructive. You're not going to write anything down for it, but I feel it's a very important demo. So they weigh, the mass is about 68.55. They mix the hydrochloric acid and the sodium carbonate. The balloon inflates as the carbon dioxide gas is generated. The reaction continues to proceed. And as we notice, the mass doesn't change very much. So again, they run the reaction and we notice the mass stays somewhat constant. Okay, let's now move on to part F, which concerns the hydrogen peroxide. So in this case, we're taking 3 mils of 3% hydrogen peroxide and reacting it with 3 mils of 0.1 molar potassium iodide. So let's observe that reaction. So in this case, we have the potassium iodide, which is a white solid, and the hydrogen peroxide, which is a colorless solution. And let's see what happens when those two solutions are mixed. Okay, so as we begin to mix the hydrogen peroxide with the solid potassium iodide, which could also be dispensed in a solution, as you notice, we're beginning to observe a color change, and we're also seeing a little bit of gas generation. In this case, this gas is entirely different from the gas products we've seen previously. The gas that's generated in this case is oxygen. So as we can see, reaction of potassium iodide with hydrogen peroxide yields a color change and gas generation. So let's write that down. So hydrogen peroxide is colorless. And evidence of a chemical reaction, we have a color change plus gas generation. Now, in terms of balancing this equation, As you can see in this case, for hydrogen peroxide leading to water and oxygen, the potassium iodide is not a reactant or product, it's a catalyst that facilitates the decomposition of hydrogen peroxide. There are also some side products from direct reaction, but we're going to focus on potassium iodide as a catalyst. The potassium iodide as a catalyst is neither consumed nor produced in this reaction. And when we're balancing this reaction, as you can see, we have two oxygens on the right, two oxygens on the left. We have three oxygens on the right. I'm going to use half notation. In this case, if I put a 1/2 notation in front of my single isolated element, which is oxygen, my count now becomes 2 oxygen atoms each. From here, we can now convert this into a normal balanced equation by multiplying all coefficients by the denominator, which is 2. This in turn gives us the following balanced chemical equation. This is known as the half notation method, and I find that it's particularly useful for reactions that generate or that involve a single element reactant or product. In terms of what type of reaction this is, we have a compound generating 2 or more elements or compounds, and this is known as a decomposition. More specifically, a decomposition reaction. So from here, we've completed our overview of this experiment. Make sure to answer all of the post-lab questions. And from here, once you finish completing your report sheet, you'll submit your full report into the Experiment 10 report submission page.